Hello, hello, hello. In this worked example, we're going to be talking about Bell states. The Bell states shown here play an important role in lots of different quantum information applications, and you'll first encounter them in a notable way in a discussion of quantum teleportation. This BSM in this diagram for quantum teleportation stands for a Bell state measurement. And when Alice wants to teleport the quantum state of one of her quantum particles into Bob's lab, the key to quantum teleportation is Alice and Bob share an entangled pair of quantum particles, and Alice needs to make a so-called Bell state measurement uh, in her lab. And what do we mean by this? What is a Bell state and what is a Bell state measurement? Let's find out. Well, to get a handle on what we mean by Bell state or Bell state measurement, it's useful to first remind ourselves of something very familiar, and that is how do you think of making measurements on a single quantum particle? So let's take our familiar example of the polarization state of a photon. And if you express the polarization state in terms of the HV basis, we can write the general polarization state as a superposition of the basis states H and V. So psi is equal to alpha H plus beta V. And then if you want to make a measurement in this basis, in practice, it's very simple. You just take a piece of calcite crystal like this, and you send your single photon in, and what will come out, you'll either get a photon coming out on the H port or the V port. And so we call this a polarization analyzer sub HV. And of course, the probability of getting either result is given by taking the magnitude squared of the coefficients. So magnitude of alpha squared gives you the probability that you'll get a click on the H port, and the magnitude of beta squared gives you the probability that you'll get a click on the V port. Now, if you want to perform the measurement in a different basis, you could define a pair of mutually orthogonal and normalized basis states, and one possible alternative set is the familiar plus 45 and minus 45 states. These are clearly normalized and mutually orthogonal to one another, and we can perform a measurement in this basis, and as a practical matter, it's very easy to do experimentally. So all you've really got to do is put a polarization rotator in front of this piece of calcite here, and you build a analyzer that measures with respect to the plus or minus 45 degree directions. You can express your quantum state as a linear combination of these new basis states, alpha prime plus 45 plus beta prime minus 45. You send the photon in, and you'll get a click on either plus 45 or minus 45, and the probability of each is determined by the magnitude of these coefficients squared. And these examples are given in terms of the specific example of a quantum particle being a photon polarization state. But more generally, we can express our quantum bits in terms of these more abstract notions of the zero and the one state. And then just a bit of notation when we make measurements on the zero and one state, and we start drawing diagrams, the standard way to represent these measurements is to draw a little meter here, and you put your quantum bit, your qubit, into the meter, and it makes a measurement, and you get either one of the basis states or the other basis states as an output of the measurement. Okay, so now let's try to take a leap from one particle measurements to two particle measurements. And here's a cartoon that of a familiar situation that we've been dealing with, where we've often been dealing with this very particular two particle photon state of polarizations HH and VV. So that's one particular two-particle state. But in general, you can represent the polarization state of two particles as a linear combination of these four different basis states. So two particles, you need four basis states to represent. 2 to the 2 is how we get to 4. Okay, so now let's think about how measurement works on these two photon states. So let's start with this particular two photon state, which is this linear combination equally weighted of HH and VV. Well, what that means is we send a photon in that two particle state into a pair of measurement devices, and they actually can be oriented at any angle, but let's consider the particular case in which they're oriented so that the thetas are both 0. So you're measuring with respect to the HV basis. So this is the H port here, and this is the V port here. Same here. This is the H port, and this is the V port. So now you send your system, your two photon system into these pair of analyzers. And what you'll find is that either you'll get clicks on the two H ports, or you'll get clicks on the two V ports, but never one of each. And if you wanted to consider a more general quantum state, which is a linear combination of all four possible basis states, the situation is not much more complicated. In that case, sometimes, if you have this term here causes a click on the H port here and the V port here. But the situation is pretty simple. It's, again, the probabilities of the different occurrences that are just given by taking the absolute value squared of these weighting coefficients. Now, suppose we want to make measurements in a different basis. In the one particle case, it was pretty straightforward, but it's going to get a little bit more complicated in the two particle case, because now any basis is going to consist of four different basis states, and you want to choose your basis to have those basis states be normalized and mutually orthogonal. So what is a good, interesting basis, alternative basis to the standard basis here? And that's where the Bell states come in. So we choose to define the Bell states in the following way. You'll recognize phi plus as the familiar single two photon polarization state that we've been dealing with a lot. But then there are three other Bell states that we can define as is shown here. And if you look at this, this is very similar in spirit to the way the plus 45 and minus 45 states were defined in the one particle case. This is sort of a generalization of that. And it's easy to convince yourself that each of these states is normalized, and they're also mutually orthogonal. So, for example, if I calculate, let's say, the inner product of phi plus with phi minus, I can write that out. There's clearly going to end up with a factor of a half out in front. And then it's going to be the phi plus the bra part is going to be an H, comma H plus a V, comma V. And then the ket part is going to be an H, comma, whoops, let's go back. These are kets. H, comma H minus V, comma V, like so. And when you multiply this out, you'll see that you get 1/2 the H acting on the HH inner product with HH is going to give a 1. And then the HH inner product on the VV is going to give a 0. So you have a minus 0, and then a plus 0, and then finally a minus 1. And so that all adds up to 0. And you can check for each of each combination here If you take the inner product of any pair, you're going to get 0. Okay, so now when we talk about a Bell state measurement, all we mean by that is sort of a generalization of the sort of thing we saw in the one particle case. We'd like some sort of device where we could start off with some two photon state that is in general a linear combination of the basis states, of the Bell basis states that looks like this. And you'd like to be able to have some sort of box where you feed a photon in that general state in, and you end up getting a click on one of these 4 possible output ports corresponding to which of the particular basis states was measured. And again, the probability of obtaining a click on any one of the ports would just be obtained by taking the magnitude squared of the corresponding weighting coefficient. Well, it turns out that it's easier said than done. If you actually try to implement a Bell state measurement of this general sort using two polarized photon states, you can sort of do it, but only partially. If you want to find out more about it, there's actually a wonderful Coursera course that you can enroll in, and the instructor is none other than our friend Alain Aspect. The famous Alain Aspect teaches a free course on Coursera, and he talks about how to make at least partial Bell measurements using combinations of beam splitters. And the theory behind it actually ends up being pretty complicated and involved, and involving a little bit of field theory. But if for no other reason, hearing his French accent makes listening to these lectures an enjoyable experience. It's really quite something. So I encourage you, if only for amusement, to Google this Coursera course, and even without enrolling, it turns out you can listen to this lecture on Bell states and Bell measurement, and it's really quite illuminating. And let me just finish up here by talking about a somewhat easier thing to do in the lab, and that is the issue of, suppose you have one particular Bell state, and you'd like to change it into another one. That's what we mean by transforming a Bell state. And that turns out to be not so hard to do. And we're going to end up making use of the Jones matrices that we talked about all the way back at the very beginning of the course when we were just talking about classical polarization states. So for example, suppose you had in your possession a pair of photons that were in the phi plus state, and you wanted to transform that into the phi minus state. Well, really all you need to do is somehow figure out a way to introduce a sign change here. And it turns out that you can do that very simply by acting on just one of the photons with the appropriate optical element. So if we look at our table of Jones matrices from the polarization tutorial, I want you to focus on this one here, which is obtained by taking a half-wave plate and orienting it with its fast axis horizontal. And in the world of quantum computing, this sort of transformation here, a matrix that looks like this, is known as a Z-gate. And if you operate, you should convince yourself that if you operate on the phi plus state on one of the photons, if you just put it through a half-wave plate with its fast axis oriented horizontally, the effect of that Z-gate acting on phi plus will be to transform it into phi minus. And another useful transformation is to take the half-wave plate and orient its fast axis at plus 45 degrees, because then you get a Jones matrix that looks like this. We call that an X gate, and if, say, you insert an X gate and have it act on, say, the idler photon, it's going to change this H into a V and this V into an H. So the effect of an X gate acting on the idler photon would be to transform phi plus into psi plus. And I'll leave it to you to convince yourself that by using a appropriate combination of X gates and Z gates acting on one of the photons, you can easily transform phi plus into psi minus. So these are the sorts of tricks that end up being very useful when you go to try to do quantum information applications. And we see that I had promised you that the this Jones matrix view of things was going to be a helpful way to think about these things, and here we're beginning to see that. So that's it for this worked example. Hope to see you again soon. Bye bye.